Hey, I found a new method. This must work very well. So now I'm going to page number 2. So this is page number 2. You can see here page number 2. And I just want to show you that now we work on the second term in the same interval like this. And all we need to do is just separate them again from A to C and then from C to B. Okay, so that's what I'm going to show you. So essentially, just be careful. From A to C, the line equation is x equals y. You can see here. Now I'm going to replace y by x squared now because originally y is squared. And then I do the same thing for the C to B. But C to B, the line equation is negative x plus 2. Okay. And then I need to replace the dy by d negative x, like that. And that's the rest of these just intervals. So once I finish this interval on the left-hand side, and I do the same thing on the right-hand side, and I add these two intervals up. So this is my final results. So it's essentially from A to C, C to B, and this is the first part. 1 over 6, just see here, that's 1 over 6 over here, and that's what I have. So once I got this, and then add them up, so this gave me negative 1. And then, after that, again, I have same difficulties to reproduce exact same answer in the back of the book. So what I did was, I just keep on integral from B to A. So when I did that, you remember B to A is the line on the x-axis, so therefore y equals 0, dy will be equal 0. So this interval is very simple, just equals 0. So there's no other things involved. So then what I have is essentially the entire integral for the second part is also negative 2. You remember first term is we got a negative 1, negative 1, and this another negative 1, so it gave me negative 2. As you can see, the third page, and we surely will get a negative 2, so which is over here. So we add them up, you get a negative 2. Now when I check the back of the book and I found out, uh-oh, something went wrong because they got a positive 2, not negative 2. So where is the mistake? So the mistake was the following. When we do the interval, we choose the pass from A to C and then all the way back to B and then eventually get to A. So that's what we had. We had then this and like that. So now, essentially, we need to know which way actually this line pass has to do. So then I move on to see whether I can use green theorem. Remember, green theorem, we have a nice expression like this. Is this on my page 4, directly page 4, the calculation. Now this appears to be simpler because I can partial q over partial x minus partial p over partial y, then do the calculation. So I need to figure out which one is my q, which one is my p. So as you can see, you should be very careful about this. The p is the coefficient of the dx, the q is a coefficient of dy. Let me show you what that means. So here is a textbook. So here I use textbook here. Did you see the first textbook that I have here? The first term is my p. Second term here is my q. So therefore when I take a derivative, and I do it carefully for this fashion. Now you can see the partial derivative is very simple. And then you will get 1 minus negative 1, so essentially dx dy, and that's the surface integral for a triangle. And the calculation is very simple. This entire thing equals 1. 2 times 1 equals 2. So therefore, final results 2. But our previous integral is giving me negative 1. As I alluded to a minute ago, it depends on which direction you do the integral. If integral is from, let's say, this is what we did, from A to C, B, and all the way back to A. So this, if we use a right-hand rule, which means we put fingers along the direction of the path like this, curl our fingers so thumb is go into the page. In other words, the final results, the surface direction, surface normal direction is negative z. However, when we do this integral over here, surface integral, we purposely choose the positive z. So therefore, the correct path you have to choose is from A to B, C, and back to A instead of top one. That's what we difference by a negative sign. And I hope you like it.